Section 3.4, Properties of Rational Functions. So a rational function is a function of the form p of x over q of x, where p of x and q of x are polynomials, and explicitly q of x cannot equal 0. Now, of course, this means that we have to consider all of the rational expressions that we see, and we have to discuss their domain restrictions from the get-go. Remember, you can't divide by 0, and so we can't have division by 0, so you got to kick out any x values that would cause the denominator to be 0. The domain of a rational function is a set of all real numbers except those that make the denominators. So now we want to find the domain for the following rational functions. So for this first one, r of x, the only thing we've got to be concerned about is the denominator. And you say x plus 3 cannot equal 0, minus 3, x cannot equal negative 3. Now we can talk about this in set builder notation. That is x such that x is not equal to negative 3. That's one way to write it, but be careful if they ask it for it in interval notation. That's of course going to be the domain is from negative infinity up to negative 3, excluding negative 3, union, kick out negative 3, up to positive infinity, and that would be the domain in interval notation. So now we have 5x squared minus 29x minus 6 cannot equal 0. I'm going to do a little bit of side work here. If I'm trying to get this to factor, I can use the AC method. That is 5 times negative 6 is negative 30. Then I'm looking for two numbers that multiply to give me negative 30, but sum together to give me negative 29. Those are negative 30 and positive 1. And so I could rewrite this as 5x squared minus 30x plus 1x minus 6 can equal 0. Then you can factor by grouping. Always remember to make sure if there's a minus there, you have to capture it with its value that it's attached to. So this will then factor as GCF of that left binomial is 5x times x minus 6 plus, we do need a placeholder, so x minus 6 has the greatest common factor of just 1. 1 times x minus 6 can't equal 0. Then we get that this is x minus 6 times 5x plus 1 can equal 0. Then we use the zero product property. X minus 6 can't equal 0. 5x plus 1 can't equal 0. That is, x cannot equal positive 6, and x cannot equal negative 1/5. And so now I have to kick out those two values. Now, if we're going to do this in set builder notation, you could say, well, all the real values x such that x cannot be 6 or negative 1/5. That's one way to do this. But in interval notation, just make sure you're in the correct order. You could also write this as from negative infinity up to negative 1/5. We kick out negative 1/5 with the parentheses, union, kick out negative 1/5, then go all the way to 6, kick out 6, union, kick out 6, up to positive infinity. And so that's how we would write it in interval notation. Well then, for function h here, we've got x squared plus 25. Well, x squared plus 25 cannot equal 0. To solve that, use the square root property, so minus 25 minus 25. X squared cannot equal negative 25. Then use the square root, that's plus minus, so that is x cannot equal plus or minus 5i. When we're talking about domains for these functions, we're only concerned about the real numbers. And so this having complex issues means we don't care. It doesn't matter. So the domain here is actually going to be all real numbers. So that is from negative infinity up to positive infinity. We need an interval notation. There we are. But that's the same thing as all real numbers. Rational functions have these things called asymptotes, or they can at least. And so an asymptote is an imaginary line that the graph approaches as x or y goes to plus or minus infinity. Now the truth is that rational functions could have three types of asymptotes. And so could have doesn't mean they'll contain all of them, but they could contain some combination of them. So the first type of asymptote that could occur is a vertical asymptote. The deal is that the vertical asymptote will never be crossed. The graph will never cross a vertical asymptote. A vertical asymptote interrupts the domain of a rational function. Specifically, what's going to happen is you'll have an imaginary vertical line where the y values approach positive or negative infinity. Now these are going to occur specifically after you have simplified rational functions as much as you can, and then once you've completely simplified, if you ever have situations where the denominator is 0 after simplification, those situations are where our vertical asymptotes will occur. Horizontal asymptotes are the thing where the functions could cross the horizontal asymptote, but it really refers to end behavior. So specifically, the graph is going to level off at some horizontal asymptote as the x values approach positive or negative infinity. And so as we go far to the right, if you have a horizontal asymptote, you're going to approach that thing but not touch it way, way out there. And then if you have a horizontal asymptote, as you approach it to the left, it's going to level out and get close to that horizontal asymptote but never touch it. Now specifically when we're talking about horizontal asymptotes, all we need to be concerned about is the degrees of the numerators and the denominator. So specifically, my 3 rules for finding horizontal asymptotes are just which one of these has the largest degree. So if the denominator has the largest degree, then specifically we're going to have a horizontal asymptote at y equals 0. If the denominator has the largest degree, we have a horizontal asymptote at y equals 0. Then, if the numerator has the larger degree, we don't have a horizontal asymptote. We may have some other type of asymptote, but it's not horizontal. And if the degrees are the same, then what you're going to do is you're going to say y equals, and then take the leading coefficients of the numerator and the denominator and put them on top of each other, and that y equals line will be our horizontal asymptote. Sometimes we get these things called oblique or slant asymptotes. Specifically, this is going to occur when the degree of the numerator is exactly 1 more than the degree of the denominator. And since the degree in the numerator is larger, you can never have an oblique and horizontal asymptote. That won't happen. You'll either have an oblique or horizontal, but you'll never have both at the same time. Oblique asymptotes will tell us what happens as the x value approach positive and negative infinity. And specifically, they'll approach some line that you can discover via division. And so let's find that. To find the oblique asymptotes, we just divide the function. And then whatever resulting polynomial, ignore the remainder, is left over, that's the equation of the line for the oblique asymptote. So if I'm given this, we want to state the domain, the vertical asymptotes, the horizontal asymptotes, or oblique asymptotes. So first, let's figure out the domain. Well, really, we just have to consider the denominator. So of course we know that 3x squared minus 11x minus 4 can never equal 0. So we should factor this using the AC method. Negative 4 times positive 3, that's going to be negative 12. Two numbers that multiply to give us negative 12 but sum to be negative 11. Those are negative 12 and positive 1. So that's 3x squared minus 12x plus 1x minus 4 can't equal 0. Then I can factor by grouping. That's going to give me 3x times x minus 4 plus, we need a greatest common factor placeholder of 1 times x minus 4. Those things can't equal 0. That is, x minus 4 times 3x plus 1 cannot equal 0. So that gives us via the zero product property, that is, x cannot equal positive 4 and x cannot equal negative 1/3. And so our domain is going to be from negative infinity up to negative 1/3, kick out negative 1/3, union, kick out negative 1/3, up to 4, kick out 4, union, kick out 4, up to infinity. That's our domain. But now to find the vertical asymptotes, we need to factor this thing completely. And so we've already factored the denominator, that is x minus 4 times 3x plus 1. But to confirm that our domain restrictions are or are not vertical asymptotes, I need to factor the numerator as well. And so I see that that's 5x squared minus 19x minus 4. Negative 4 times 5 is negative 20. Two numbers that multiply to give me negative 20 and sum to be negative 19. Those are negative 20 and positive 1. So we get 5x squared minus 20x plus 1x minus 4. Then that is going to give me 5x times x minus 4 plus a placeholder of a GCF of 1 times x minus 4. That's then going to give me x minus 4 times 5x plus 1. So this factors as x minus 4 times 5x plus 1. At this point, we need to reduce. Notice that x minus 4 divided by x minus 4 is 1, so I'm left with 5x plus 1 divided by 3x plus 1. And so the fact that we factored out some stuff changes what our vertical asymptotes could be. So specifically, now I look at whatever the denominator is of my factored rational expression, and whatever would make it 0, that's where I have vertical asymptotes. So specifically, my vertical asymptote is going to be x is equal to negative 1/3. And so I have a vertical asymptote at x equals negative 1/3. Then, for horizontal asymptotes, we just need to make a degree argument. So, which has a higher degree? Well, notice that we have, at this point, reduced degree 1, degree 1. Since they're both degree 1 polynomials, then specifically, we have a horizontal asymptote at y equals the ratio of coefficients. Specifically, the coefficients are 5 and 3. So, 5 over 3 is my horizontal asymptote. So specifically, y equals 5/3. So that's my horizontal asymptote. The moment that we have a horizontal asymptote, we know that we do not have an oblique. So there is no oblique asymptote if we have a horizontal. If we have a horizontal, there is no oblique. So you'll get one or the other, but you can't get both. It's possible that you have neither, though, so be aware of that. Something else I want to make note of here is that once you find your vertical asymptotes, notice that we still had other domain restrictions, right? We still had the domain restriction of negative 1/3. But if it's not a vertical asymptote, what is it? Well, specifically, it's going to be what we call a hole. And so I'm just going to go ahead and talk about this for a moment now. Specifically, we're going to have a hole at x equals 4. And so because that was the value that got kicked out when we reduced, specifically there's going to be a hole at 4. And if you wanted to know the exact ordered pair where the hole occurs, you take that 4 and plug it into the function, and so plug it into this reduced function. That's going to give us 5 times 4 plus 1 over 3 times 4 plus 1, which is going to be 21/13. And so specifically, not only is there a hole at x equals 4, but it's specifically going to be at the ordered pair 4 21/13. And when we graph this, it's just going to be an open circle there. So let's do all this again. So we want to figure out the domain, vertical asymptotes, horizontal asymptotes, oblique asymptotes, and if there's any holes, let's mention them. So first we need to find the domain, that is x squared plus 3x minus 4 cannot equal 0. X squared plus 3x minus 4 will factor as x plus 4x minus 1. That then means that via the zero product property, x cannot equal negative 4 or positive 1. And so our domain is going to be from negative infinity up to negative 4, excluding, union, excluding negative 4, up to 1, union, excluding 1, up to positive infinity. Now we need to talk about vertical asymptotes, but to find those, we need to simplify this completely. So that means I need to factor the rational expressions first. That is, we already know that x squared plus 3x minus 4 factors as x plus 4 times x minus 1. And we have that x cubed minus 1 is a difference of cubes. Specifically, for the sum and difference of cubes, writing down two formulas, if I have a cubed plus b cubed, that is a some sign times a squared assign ab assign b squared. Now I write it like this because then my signs come from SOAP, same, opposite, always positive. So specifically, if I have a cubed plus b cubed, that is going to be a, same sign as plus, opposite sign is minus, and then always positive is always positive. But if I change that, and I have a cubed minus b cubed, then same sign as minus, opposite sign is plus, and then always positive is, of course, always positive. And so that is the sum and difference of cubes formula as a reminder. Then to factor this, x cubed minus 1 is a difference of cubes because its cube root of 1 is 1, and so x cubed minus 1 is the same thing as x cubed minus 1 cubed. So that is x, same sign, minus 1 times x squared, opposite sign plus, 1 times x is x, plus 1 squared is 1. And so there we have it. Now let's reduce as much as possible. We get x minus 1 divided by x minus 1 is 1, and we're left with x squared plus x plus 1 divided by x plus 4. Well, then our vertical asymptotes are going to be where our reduced denominator is 0. So we have a vertical asymptote at x is equal to -4. Now because I have that vertical asymptote, that also tells me that I get a hole at the other domain restriction. That hole is going to be at x is equal to 1. And specifically, if you needed the ordered pair where the hole is going to be, plug the 1 back into our reduced function. 1 squared is 1 plus 1 is 2. 2 plus 1 is 3. So this is the ordered pair 1, 3 on top. 1 plus 4 is 5. So 1 3/5 is the ordered pair where we'll have a specific hole or open circle on the graph. Now the question, do we have a horizontal asymptote? Well, when do we have a horizontal asymptote? We have a horizontal asymptote when the denominator has the larger degree, but that's not true. We could also have a horizontal asymptote if the degrees are the same, but that's also not true. The degree on top is 2, the degree on bottom is 1. So there is no horizontal asymptote. But specifically there is an oblique asymptote. And so since there is, we have to actually find it. Now how do we find an oblique asymptote? We just do division. And so I'm just going to do division with what's written here. Because this has a linear divisor, we could use synthetic division. If it wasn't linear, you would need to use long division. But since it's linear, let's do synthetic. So the 0 is -4. The coefficients are 1, 1, and 1. And so we're just going to do the division and ignore remainder. We don't care about the remainder. So bring down the 1. -4 times 1 is -4. Add down, that's -3. And technically, to finish the process, -4 times -3 is +12. But then the remainder is 13. But we don't care about the remainder. And so the divisor that we get is going to be 1 degree less than what we started with. So instead of x squared, it's x. So that's going to be y is equal to coefficient of 1x minus 3. And so I claim that this is our oblique asymptote. We don't care about the remainder right now. Y is equal to x minus 3 is the oblique asymptote. And so what we'll do is we'll graph that thing with a dashed line through y equals x minus 3, and we'll know that at the end behavior you will approach that line. So now we want to look at all this information, and we want to find the domain, the range, the x-intercept, the y-intercept, the vertical asymptotes, the horizontal asymptotes, or the oblique asymptotes if they so occur. So let's see what we've got. Well, first off, with the domain, we can just call out the domain. But notice that these dashed lines are actually labeling things for us. Specifically, this is a vertical asymptote. And so that's the vertical asymptote, y equals 0. And so I'm actually going to do this in an odd order, but my vertical asymptote is y equals 0. There's only one. Then let's look for horizontal asymptotes, but I don't see any, so there are none. And we also don't see any holes. And so remember that when I mentioned holes earlier, we're literally looking for an open circle somewhere, but we don't see any open circles, so we don't have any holes. So that means that I actually now know my domain. My domain kicks out the vertical asymptote values, and it would kick out any holes, but since we don't have any holes, we just have a domain from -infinity up to 0. Don't include 0, union, don't include 0 up to +infinity. Now the range here, we just need to do our horizontal line and see what all we touch, but we touch everything, so our range is actually going to be all real numbers here. Then we want to find the x-intercepts, but notice that I have 2. They're right there and there. Those are -2, 0, and 2, 0. If they asked for the integer values, you would just give the integer values. Do we have any y-intercepts? Well, because we have a vertical asymptote on the y-axis, we do not have any x-intercepts. They don't exist because we'll never, ever, ever cross a vertical asymptote. And so there are none. Then we need to talk about this oblique asymptote. Well, I described an oblique asymptote, but I claim this is actually an oblique asymptote now. Notice that this dashed line just keeps on going here, and it keeps going here. And as we get there, we'll see that the graph approaches those oblique asymptotes as we continue. Well, how can we find that? Well, it's just a line. And so somehow I need to find out the equation of that line, but of course this is the origin, 0, 0. And since that's the origin, and we also have the other ordered pair, 2, 8, then I can use that information to find the slope, where the slope is really 8 minus 0 over 2 minus 0. So my slope is 4, and my y-intercept is 0, and since I have a slope and a y-intercept, then I know that my oblique asymptote is the line y equals 4x plus 0, but I'm not even going to include the plus 0, so there we are. Now let's say we want to graph rational functions using transformations. The truth is that all our old transformations still work in the exact same fashion. We just have to remember what's inside the function and what's outside the function. Inside the function is, of course, horizontal. Outside the function is vertical. In general, we will frequently see, if we're dealing with these transformations, one of two formats. That's either going to be 1 over x, which is going to look like this. Notice that we have a vertical asymptote at x equals 0. We have a horizontal asymptote at y equals 0. Or we may see 1 over x squared. Well, 1 over x squared is going to be slightly different. It looks like a volcano. And so notice that once again we have a vertical asymptote at x equals 0. And we have a horizontal asymptote at y equals 0. And just as a quick error checker, remember that we could find the domain restrictions, but both of these have a domain restriction of 0. And since they are completely reduced, that's where my vertical asymptotes are, x equals 0. Then for the degree arguments, that tells us where the horizontal asymptotes are. Here, our degrees are larger on bottom for both. That means that specifically our horizontal asymptotes are y equals 0. So now let's say that I want to find via transformation -3 plus 1 over x. I'm going to change the way it's written so that it looks more like my general transformations. And I'm going to put the x stuff first, 1 over x minus 3. Well then, inside the function would be in the denominator there. But notice that this is outside, and so that's vertical stuff. And so what that is that's actually going to go down 3. That's all. So the transformations that we see are down 3. So specifically, if this things go down 3, that means that I'm going to have a horizontal asymptote at y equals 3. Our vertical asymptote is still x equals 0. And then because I've had no reflections, truthfully, I get this. Now I've sketched it very quickly and very poorly. If I wanted to get a better sketch, I really should be picking some values, plugging them in, and plotting some ordered pairs. But in general, this is the idea. Once we have that, we already knew the domain. The domain was everything but 0. That was negative infinity up to 0 excluding, union excluding 0 up to positive infinity. The range here is, notice that for the range, it never actually crosses this horizontal asymptote, although sometimes it could, but for this one it won't. And so our range is going to go from negative infinity up to where the horizontal asymptote now is, which is -3, excluding, union, excluding -3, up to positive infinity. And then of course we said that the asymptotes are where? They're specifically at y equals -3. We're going to go back in a moment and check this algebraically, but I'm just doing it via transformations. And we also have the vertical asymptote x is equal to 0. Let's go back and let's adjust this a little bit. So let's put this as a single rational expression as opposed to this addition stuff. And so how could I do that? Well, I can multiply by 1 in disguise. My 1 in disguise would be x over x, so it gets a common denominator. Then I get 1 minus 3x all over x. At this point, this confirms everything else we found because we know that our domain restrictions are x can't be 0. We also know that because the degrees, and I'm going to rearrange this, -3x plus 1 over x, because the degrees are the same, then our horizontal asymptote is going to occur at the value y equals the ratio of the coefficient, where specifically the coefficients are -3 and +1, and so y equals -3 over +1. So algebraically we just confirmed what our transformations showed us. Now we want to do all the same things. We have -2 divided by x minus 2 quantity squared. Well, I'm going to readjust this for a moment, and let's say I wrote this as -2 times 1 over x minus 2 quantity squared. Well, notice that what's happening here is this is outside, and so that's a vertical stretch or compression. Specifically, it's going to be a vertical stretch and reflection across the x-axis. Then notice this is inside the function, so that's going to be a horizontal shift, specifically opposite, so this thing goes right 2. Right 2. And then we can remember that this x squared function, if I had 1 over x squared, what does it look like? It's going to look like the volcano. And so a handful of things happen. It gets turned upside down, so it's going to be an upside down volcano. So do a little bit at a time. -1 over x squared is an upside down volcano. Maybe a sinkhole would be a better descriptor. And then we see that it's a vertical stretch, which means it's going to get taller and skinnier, and it's going to shift right too. But that's really just going to move that that vertical asymptote that we have. So now our vertical asymptote is going to be right too. So here, the horizontal asymptote didn't move since we didn't shift up or down, but it is going to get taller and skinnier, so just something like this. And then we approach the horizontal asymptote, and we also approach the vertical asymptote. Well, then we can find the domain and the range. The domain is everything but what would cause the denominator to be 0. The only thing that would cause the denominator to be 0 is 2, so our domain is from negative infinity up to positive 2, not including, union not including 2, up to infinity. Our range here, notice, is really all the values below 0. So that's going to be from negative infinity up to 0, but because of that horizontal asymptote and we see we don't cross, this is not included. Then our asymptotes, where do they occur? They specifically occur at x is equal to 2, that's our vertical asymptote, and the horizontal asymptote y equals 0. Now, how do we know this to confirm? Well, after we've completely reduced it, we know anything that would make the denominator 0 is a vertical asymptote. And then for the horizontal asymptote, we see that our highest degree is on the denominator, which means that we automatically get y equals 0 being our horizontal asymptote.